myself Dr. Ananda Tirtha B. Gudi, Professor and Coordinator PG Studies, Department of Electronics and Communication Engineering, Global Academy of Technology, Bangalore. In digital electronics session, we are going to discuss parallel binary adder today, and under that parallel binary adder, first thing we are going to see parallel binary adder circuit construction using half adder and full adder blocks, and in continuation with that we are going to see the parallel binary adder circuit construction using only full adder blocks. After that, to give the requirement, to fulfill the requirement of this particular digital electronics part, half subtractor and also full subtractors are discussed. Finally, till date in previous sessions and also in the present session, whatever we are going to discuss, combining the gist of our discussion, we are showing a little bit interest to make a small application type of project, that is nothing but the combinational logic circuit. Especially in this particular session, we are going to discuss a combinational logic circuit which is helping us for 7 segmental LED display, and that circuit we are calling it as a decoder circuit, and that decoder circuit is fully constructed with the basic gates. Parallel binary adder. An n-bit adder is a circuit which adds 2 n-bit numbers, say A and B. Second point, in addition, an n-bit adder will have another single bit input which is added to the 2 numbers called a carry in, that is C in. The last one, the output of n-bit adder is an n-bit sum S and a carry out C out bit. Now we are going to see here the 2 block diagrams. One is half adder block diagram, another one is full adder block diagram. In this half adder block diagram, here we are going to see the 2 variables A and B. When you are going to add these 2 variable values like 0 0, it may be 0 1, it may be 1 1, and it may be 1 0. Any value of A and B, if you are going to add, the added value we are going to get as a sum. In the last case, when A is also equal to 1 and B is also equal to 1, then automatically what happens, we are going to get a 1 0. 1 plus 1 is a 2. In binary, we are going to say it is 1 0. That 1 is acting like a carry, and some value is just it is denoted as 0. That sum value 0 and carry, what we are going to get 1, it is displayed on the carry line at the output. So, but in this particular another circuit, full adder, here in this disadvantage, or in this what we are not saying is the any carry previous stage, any carry is there, or input carry facility is not provided here. Only A and B 2 variables can be added and the additional value, and if carry is generated, that carry out facility is provided with the full half adder. Now in the full adder, what is the difference with the half adder is, once again the 2 variables are taken as input, and one carry out terminal is provided here, and one sum output terminal is provided here, and one more input terminal, a special input terminal is provided for this full adder, that is nothing but the carry in. So here only 2 input terminations are there and 2 output terminations are there. In this full adder, 3 input termination and 2 output terminations are made available. If the binary numbers being added are A3, A2, A0 1 and A0, and along with that B variables B3, B2, B1, B0 is there, say for example. Then the A0, A1, A2, A3 we are going to write, it is a least significant bit and it is a most significant bit, and the next variable B, least significant bit is here, and this most significant bit is here. Now if we are going to use a parallel adder, then simultaneously I can add, okay, A0 and B0, and sum is recorded here and it is available as S0. If any carry is generated, along with that carry, okay, we are going to take here, and A1, B1 and carry generated from the previous stage is also taken into account for addition, and S1 is looks to be some value of such additional value, and if any point of time once again the carry is generated, that carry is taken forward to the when we are adding A2 and B2. Along with that if carry is generated in the previous stage, that also taken into account, and A2 B2 along with that carry if we are going to add, so then we are going to get S2 as outcome, and there is a sum, and once again the carry is generated, that carry is taken to the next block where when we are adding the A3 and B3. Along with that the carry is also going to be added, then the final output we are going to call it as a sum value S3, and any carry is generated while adding A3, B3 and the previous carry taken forward, and the S3 is taken as sum, and that carry is taken as the last bit S4. So here in this particular thing only we have taken the 4-bit operation. The carry out bit of one stage of full adder is used as carry in, that is input to the next stage, that we already discussed here. And the last point, in general an n-bit parallel adder can be built out of n full adder blocks, or sometimes we are going to construct with n-1 full adder block and 1 half adder block. Such one circuit is shown here with 4-bit addition facility. So now this particular circuit we can, or block diagram we can call it is a parallel binary adder circuit using half adder and full adder blocks. Here 3 full adder blocks are taken, and the last one here right extreme right we are using only 1 half adder, because while adding the A0 and B0, these are the least significant bit, the carry may not be there, this carry is not coming from anywhere. So therefore the half adder may be sufficient at this level. By considering this half adder as the to add the least significant bit of A and B, we are going to get some value. When adding A0 and B0, if any carry is generated, that carry is made available and the sum value is recorded as S0. That carry is taken as a input variable for the next cascaded stage where we can add A1, B1. Along with that, the carry in which is coming from the out of this half adder is also considered for this full adder, and by adding these 3, the sum whatever it is going to be generated, it is indicated as a S1, and while doing so, if any carry is going to be generated, further that carry is connected to the next cascaded stage. And in this once again the A2 and B2 values are taken as an input. Along with those 2 variable values, input values, the carry of the previous stage of full adder is also taken into account, and all these 3 values are going to be added, and the additional value or the sum is noted as S2, and any carry is generated, that carry is made available at the output of this particular stage, and once again that connected to the output terminal, and that output terminal available value of carry out is made available as carry in for the next or the last stage of this 4-bit adder circuit. So in the last full adder, the B3 and A3 values are going to be added along with the carry in which is generated from the previous block. So that is also taken into account, and the sum value can be treated as S3, and the final carry out, whatever we are going to see further, we have not connected anywhere because we are swapping it to the 4-bit addition. Then this carry, either it may be a 0 value or it may be 1. So if it is 1 is generated, then that carry 1 is taken here. So already we have seen this addition, A0 B0 is sum is S0, carry already generated anything. So then this S1, if any carry is generated, it is taken forward, and these two addition along with that carry is S2, and finally that S4 is output. Here only the thing is the first stage, okay, to add the least significant bit A0 B0, we can consider the half adder. There is no necessity of considering the full adder circuit at this particular block stage. So next, if at all we want to use the all full adder blocks only to construct the parallel binary adder, so then the circuit will become, block diagram will become like this. So this particular block diagram, which is shown here to add 4 bits, is considered as parallel binary adder circuit using only full adder blocks. Here whatever we have seen in the last circuit, the cascading of full adder blocks are here, and only the thing is when in the least significant bit of A and B, so that is A0 B0, when we are going to add, where to generate S0 some value in this particular block, instead of half adder, here we have taken the full adder. The only thing is we should have to consider very much care must be taken here, because if carry is should not keep open here. So because if nothing is made available, then the circuit may not work properly. So therefore, because carry is not taken from anywhere, it is a because it is the very first stage, only A0 and B0s are going to be added here. Therefore this carry input terminal of a full adder must be connected to the ground, otherwise it may lead to some other problems. So therefore particularly this carry in is grounded, and such a full adder circuit, when we are going to say the carry is grounded, then automatically this carry in very first block, okay, is going to become equal to 0. Therefore B0 and A0, when you are going to add along with that C in value as 0, the value is not going to be altered because of the introducing this particular point which you have grounded. So therefore the result is unaltered, but additional value of B0 and A0 is giving the S0. If any carry is generated, that carry is made available on this particular line. So that carry out of the first block is made carry in for the next cascaded full adder block. Here A1 B1 is once again it is added, S1 is taken as a result, and because of the additional value of these 3 variables, A1 B1 and also carry in of the previous stage, once again the carry may be generated. That carry is taken forward as a input to the next block. Similarly in this A2 B2 are added along with this carry, then S2 is taken as a sum, and the final carry of this block is made available here. So that is taken as a carry in for the last block when we are adding A3 and B3. So then finally whatever the carry out we are going to get, that is marked as S4. So here the sum is taken as S3. So the same thing here, because even though the 0 is added as carry in, it is result is unaltered. S0 remains, because sum of these two, whatever the value we are going to get, that we have taken as a S0 value, and remaining thing is looking like same like the previous block. Now by taking an example of some numbers, binary numbers. So here A0, A1, A2, A3 is taken as 1, 1, 0, 1. So it is the least significant bit and it is a most significant bit. And in case of B variable, so this is B0, B1, B2, B3 are considered as B0 equal to 1 and B1 equal to 1 and B2 equal to 1 and B3 equal to 0. When we start adding the things in the very first half adder block, so then we are going to see here one B0 value is 1 and A0 value is 1. both are added here. 1 plus 1 is equal to 1 0. So that it is nothing but 2. 1 plus 1 is 2. That 2 in the binary we are going to write it as 1 0. Then 0 is considered as some value, and then that carry 1 is taken as carry. And that carry, whatever it is generated at the output of the half adder, is taken as a input to the next full adder. Once again, for the next full adder, the B1 value and A1 values are once again looking like 1 and 1. So 1 plus 1 is 1 0 plus 1, that is 1 1. So totally it is 3. So 1 1. The final output is 1 plus 1 plus 1, that is 1 1. In binary it is nothing but decimal equivalent of 3. So therefore that 1 is considered as carry, and the right most or least significant bit of 1 1 is taken as sum for the as S1. Then once again that output is taken as input to the another next stage half adder. Then here the A value in the next stage, A value is treated as A2 is treated as 0, and B2 is treated as 1. B2 is treated as 1. So that these two values are added along with the carry what it is made available here. So then 1 plus 1 is 0 plus 1 is 2, that is 1 0. So that 0 is considered as the sum S2 value, and 1 is taken as carry out from this particular full adder stage, and that carry out is nothing but it is input to the carry in to the last full adder stage. So here A3 value is 1 and B3 value is taken 0, but here already carry is available as input. So therefore 0 plus 1 is 1 and 1 plus 1 is 2, that is 2 in the binary we are going to write it as 1 0. Therefore that 0 value is made available at S3, and that 1 is taken as a final carry out, that is S4. So here that carry is indicated here, whatever the carry red mark is here, so the red marked one is here, but finally we are going to mark here it with a green. So that is S4 is at this position it is there. So now the final value is 1, this is 0 1 0 0 1. From this most significant bit is 1 and least significant bit is 0. So it is all this sum S0, S1, S2 and S3 are made available with the main significant bit S4 value as 1. Similar example, if we are going to take to construct the full adder, then automatically 1 1 are taken as B0 and A0 values, and carry in value is equal to 0. So 1 plus 1 is 1 0, that 0 is made available here as a S0 and carry is 1. So that 1 is considered taken for the next stage while adding the B1 and A1 values. Along with that the carry is also added. 1 plus 1 is 2, 2 plus 1 is 3. So that 1 1 in binary, the 1 1 is nothing but 3. So therefore the 1 1 value, least significant bit 1 is taken here, and most significant bit out of 1 1 is taken as a carry here. That carry is once again it is taken as input to the next stage. So here the A2 value is equal to 0 and B2 value is equal to 1. Already this carry is made available here as 1. So then 1 plus 0 is 1 and 1 plus 1 is 1. That is 1 plus 1 is 2. So that 1 0 is a equivalent value in binary for 2. So then automatically the 0 is considered as a sum value and carry is taken out from this block. That carry is made available as input for the next full adder. So in the last full adder, B3 value is 0 and A3 value is 1. So along with that, if you are going to add carry, 0 plus 1 is 1, 1 plus 1 is 2, that can be represented as 1 0 in binary. So that 1 is made available as carry and the output termination of carry out, and S3 is considered as 0. So that carry out we are indicating as S4. As in the final value is nothing but S0 value is 0, S1 value is 1, S2 value is 0, S3 value is 0 and S4 is equal to 1. So therefore finally the addition value, sum value in binary we are going to indicate like this, 1 0 0 1 0. Next. So somewhere if you are not going to discuss the half subtractor and full subtractor, then personally we feel this logic gates or this digital electronics study till what we have discussed, it looks to be little bit incomplete. So because for multiplication, if for example 7, if we are going to multiply it by 5, then the answer we can say it is 35. 7 number can be added 5 times to get 35. So similarly, when we come to the subtraction, so 36, how many number of times the 36 value can be divided by 7? So go just to start subtracting 7 in 36. So how many number of times you can subtract means 5 number of times you can subtract 7 in 36, and remainder looks to be 1, because 36 plus 35 plus 1 is 36. So 5 times easily we can divide, and if the given number is 36, then 1 we are going to get a remainder. So therefore for division and subtraction operation, when it comes to the microprocessor and computer, the subtractor operation looks to be very important one. So that's why we feel this study, little bit study of this half subtractor is more relevant at this stage. So therefore we'll see the half subtractor. So here A and B are the two variables, and here our intention is to find out the difference between A and B. So both are 0 0, hence the difference value is 0. Nothing is borrowed to achieve the difference subtraction computation. So that's why the borrow is also equal to 0. So now if A is equal to 0 and B is equal to 1, so then automatically we should have to borrow 1 to this. So then automatically it becomes 1 0. So in 1 0 is nothing but 2. Out of this 2, if we are going to subtract 1, the difference value becomes 1. So and then the borrow value is going to become 1. Similarly here 1 minus 0. So 1 minus 0 means, because it's a higher value is there at A and 0 is there at B, then immediately we can say the difference value is 1, but we have not borrowed anything, hence the borrow value becomes 0. So 1 1. So 1 A value is 1, B value is also 1. So 1 minus 1, it leads to difference is 0, and there is no, once again there is no necessity of borrow. So after that this truth table, drawing of this truth table, now we are going to design the subtractor circuit or realization of this half subtractor. So once again just see here the borrow, here only this A bar B, A bar B is nothing but the borrow value, that is here it is indicated 1, here the 1 is there, here also 1 is there. So sum of products, that concept if you are going to consider, then A bar B plus A B bar is nothing but the value of a difference, because in the difference only in 2 positions in the table we are seeing 1. So for this one we are going to say the product value A bar B, and for this A B bar, if you are going to sum these 2 values, then it is nothing but the difference value, that A bar B plus B bar A B bar or A B bar A, that is nothing but the exclusive OR operation. Already we have seen many number of times the exclusive OR operation. So therefore the difference value we are going to code it as A exclusive B, and borrow value is A bar B. To achieve these 2, A and B, 2 variables are taken at the input of XOR gate, and output of XOR gate is giving the difference value, and A is straight away taken from this one, and just this is A bar. So here A bar B, so this NOT gate should be connected to this B. Okay, so this NOT gate should be connected to the A line, and we are going to see here actually the circuit should be like this. So this is the A and B, these are the A and B values, here XOR gate is connected here. So then this final value is a difference, that difference value is equal to A exclusive B, and from A, this is A bar is there, so that's why this NOT gate must be added to this, and B must be taken as it is, and NOT gate AND gate must be put here after this NOT gate, and here this particular thing is A bar and this is B, so A bar B is the borrow value. So this we are able to do like this. Small changes we should have to make in this to make it proper. So next, full subtractor. While doing the full subtractor operation, here we are taking the three variable values A, B, and also we are considering the B in, that is that value, and the difference and borrows are taken like this. If all the three values are 0, 0, then difference value is also equal to 0, borrow is also equal to 0. So then if 0, 0, 1 is there, then the difference is going to become 1 and borrow is also going to become 1. If 0, 1, 0 is there, then difference is going to become 1 and borrow is also going to become 1. If the numbers are like this, A is 0, B is 1 and this B in is also 1, then difference is equal to 0 and borrow is equal to 1. Similarly 1, 0, 0, the difference is equal to 1, borrow is equal to 0. So next level is 1 minus 1 is 0, 0 minus 0 is 0, hence there is no necessity of there is no difference generation and there is no borrow. The last stage, if you are considering all the three variable values are like this 1, 1, 1, then automatically difference value is also going to become equal 1 and borrow value is also going to become equal with 1, and that difference if you are going to see 1, 2, 3, 4 places it is showing 1, 1. If you are going to write the SOP, that is sum of product values, where there is the one is there for this and this and this and this, and if you are going to make an equation after simplification of that equation, just like what we have seen in our full adder, then the difference equation or Boolean expression for difference, we are going to get A exclusive B exclusive B in, and for borrow in position 1, 2, 3 and in 4 positions we have 1, 1, 1, and for that if we are going to write the Boolean expression of in the form of sum of products, and after simplification we are going to get A bar into B exclusive B in plus B into B in. So if we are going to realize the equation, realize the Boolean expressions using gates, then the full subtractor, this is the solution what we said, no, that is the SOP value for where the 1, 1, 1 is there in the table that we have taken, and after simplification we are getting A plus B in. Similarly on 4 positions of the table for B borrow out also it is there, so SOP is equation is drawn, and after simplification we are going to get A bar into B plus B exclusive B in plus B into B in. So the same thing can be executed here with 2 exclusive OR gates. The difference value A exclusive B exclusive C in is taken, and similarly by making use of this these 1, 2, 3, 4 basic gates operation, the B out. So here the A is taken through this one as A bar, and here exclusive this exclusive operation out B in into B, that exclusive value is available here, that is taken as a one input of this exclusive OR gate, and B in and here B multiplication value is taken as one input, then the final B out is successfully seen as the equation outcome this value, whatever we are seeing in the previous slide. So then we are able to say this is the full subtractor using basic gates. Now if you already we have seen the NOT gate operation and other gates operations also. So NOT gate can be, we have already discussed NOT gate construction can be done with the transistors, and other gates construction with diodes and transistors we can do, and sometimes we may be using transistor logic also to construct gates. So if you want to do a simple project by knowing the basic fundamentals of this digital electronics and logic gates, then these chips are available in the market. So just by looking into the internal construction, this is the NOT gate or inverter. The number is 7404. Here it is a 14 pin IC. Most of the time the 7 pin is treated as a ground pin and 14 pin is treated as VCC. Here plus termination of the battery is given, and here negative termination of the DC battery is given. And because these internal devices through which we are getting the operation of these logic gates are active components, therefore the source is required to keep this in these gates, internal gates, in the active mode. So therefore the source is required. Here in this particular NOT gate chip, there are 6 NOT gates are available, and these NOT gates, first NOT gate is made available between pin number 8 and 9. Here is the notch is there. So usual practice is from the notch we are going to read the pin number 1, 2, 3, 4, and it gets end with 7, and 8 to 14 pins are read like this. So between 8 and 9 one NOT gate is there. Output termination is at 8, input termination is 9. Similarly 10 is the output termination and 11 is the input termination, and here 12th is the output termination of this particular NOT gate, and 13 is the input. Like that, similarly another 3 gates are connected here. Totally it is 6 NOT gates are there in the internal construction of this particular IC 7404. So in this here it is the internal construction of the AND gate is shown, that is 7408. In this 4 AND gates are made available here. So because the 2 input and 1 output is there, so out of 14 pins, 2 pins are already used for to give the source, and only the remaining pin 12 pins are available. So 3 pins for each gate multiplied by 4 gates, remaining 12 pins are used like this. So this is the output pin, and these 2 are the input pins for this, and pin number 6 is nothing but the output pin, and 4, 5 are the input. Here 1 and 2 are the input and 3 is the output. In this 13 and 12 are the input pins, where the one pin number 11 is treated as output pin. Similarly here for the number of this is 7408. Similarly here 7432 is nothing but the OR gate integrated circuit chip. So now here pin number 14 and once again pin number 7 are used for supply, and here the 4 gates are made available because the 3 terminations are required. Here this is 7400. Here we are seeing the NAND gate inside, and here also the 2 input termination, 1 output termination, such 4 gates are accommodated. Here this NOR gate. Here also only the NOR operation, but 14 pin IC is there. Inside 1 pin for the each gate, 1 pin for output and 2 are for input. Such to cover the 12, just by covering 12 pins, 4 gates can be accommodated. Here it is XOR gate. Here also 2 inputs and 1 output pin is there for each and every gates. Such 4 gates are accommodated within 12 pins, and 14 and 7 are treated as source pins. But here already in most of the time we have taken 4 input NAND gate, and okay, here also there is a 7420. So here 1, 2, 3, 4 inputs are there. Here 1, 2, 3 inputs are there, 1 output is there. Here also for this AND gate, NAND gate, 3 inputs are there, 1 output is there. 3 input NAND gate, and so for 3 input NAND gate only 3 circuits can be accommodated within the 12 pins. Here the 4 inputs are there, 1 output is there. When the input pin is increased, because of that reason, if you want to construct or build the 4 input 1 output type of NAND gate, then only 2 gates, such gates can be accommodated. Such 17420 is shown in here. Next, now as a mini project, if you want to do a 7-segmental LED display, once again we are going to say there are 2 types of 7-segmental displays are available. One is common cathode, another one is common anode. So here the LEDs are placed like this. So this is LED A, and this is for responsible for B, and this is for C, and this is for D, and this is for E, and this is for F, and this is for decimal point. So by considering only majorly 1, 2, 3, 4, 5, 6, 7. So this particular thing we are going to call it as a alphanumeric display. Here all diodes, LEDs, cathodes are joined. Okay, all cathodes are shorted and it is connected to the ground point. Two places we have made the facility for ground. So this point and this points are made common. So along with that, here we are seeing D, C and E, A, B. So to glow this segment, here we should have to give the input high value, and to glow this segment we should have to give B high value with respect to the common ground point, and to glow this F we should have to give the high with respect to this ground, and to glow G we should have to give high with respect to ground. Similarly, C must be made high to glow this particular segment, and to make it glow this D, here D must be made high, and to E to glow E, this particular diode, E must be made high with respect to ground. So in this particular chip we have seen the common all cathodes are made common. That's why this is common cathode 7 segmental display. To achieve this kind of thing, we are going to select A, B, C, D 4 variables, and these are the segments A, B, C, D, E, F, G. These are 4 segments. These are the segments and these are the 4 inputs. Capital A, B, C, D are the inputs, and this small a, B, C, D, E, F, G are treated as individual segments of 7th segment LED. So now if you want to generate 0, then all A, B, C, D input must be equal to 0, and here only the G should not glow. In this case G should not glow here, except, see, go back and see here, if you are this G is not going to glow, then obviously we are going to get only the glowing of the other 6 LEDs, and those 6 LEDs are going to give the effect of the 0 that we are going to see in the next slide. Similarly, if we want to make the numeric value 1 display, then here the segment only this B and C should glow, and all other segments are marked 1. Wherever we have marked 1, here these segments should not glow. To make it 1 display, alphanumeric this one, okay, only one number 1, so then automatically these 2 segments should glow. Similarly for 2, to make it to glow as number 2, then automatically this A should glow, and B should glow, and D should glow, and this E should glow. So when these 4 segments are going to glow, then automatically it is going to give the effect of number 2. And if you want to display 3, then automatically in this A should glow, and B should glow, C should also glow, D should glow, and the last G should glow, and only E and F should not glow. Similarly for to display the number 4, here this A should not glow, here only the B and C should glow, and finally F and G should glow, and all other LEDs segment should not glow. For 5, number 5, the A should glow, and C should glow, and D should glow, and F should glow, and G should glow. Here the other segments, excluding this, other segment should not glow. So 6, okay, same thing we are going to see here. Whichever the segments we don't want to switch on, that segment must be treated as high, and all other segments are treated as low. So to achieve that, here the combination all are 0, and 0, 0, 0, 1, and 0, 0, 1, 0. This is this kind of a combination of ABCD has been selected. The last combination to glow, the 9 is taken as 1, 0, 0, 1. So this table is first prepared, and then we are going to write the Boolean expression of each output function can be written. So this a special min term type of thing we are going to write here, and construction of constructing the K maps, corner map for each output term, and then simplifying them to obtain the logic combination of inputs for each output. So here this A, B, C, D are taken. Wherever here A, B, C, D are the inputs, and where we have marked the zeros, no, those segments, okay, values are marked here. By using K-map technique, we are able to generate the expressions for a segment glow, a plus c plus bd plus b bar d bar. So here these b is equal to b bar plus c bar d bar plus cd, and c is equal to b c bar plus d. D, where if you want to glow, then b bar d bar plus c d bar b c bar d plus bc, and E is equal to b bar d bar plus c d bar. F is equal to a plus c bar d bar plus b c bar plus b d bar. G, if you want to glow, then the value a should be a plus b c bar plus b bar c plus c d bar. If these are if you want to glow, this should be the equation. For to glow B segment, this should be the equation. So these are indicating the LEDs, and these right side equations are indicating the values of the variables a, b, c, d. So to make it here, actually the output what we are going to get here should be high, because if it is high, then only the common cathode LED segment, that particular diode can be glown. So therefore here we are going to use the AND gates, whatever the variables are there, no, that we are going to use the AND gates, and all these 1, 2, 3, 4 values are going to be added here with the OR, and then the output which is available, it should be high to glow this particular segment. So depending upon the number which we are going to want to glow, then which we want to generate 1, 2, 3, 4, 5, 6, 7, 8, 9 and also 0. So depending upon that, we are going to see the glowing of these particular segments. So the combinational circuit which is drawn to using 4 inputs ABCD and 7 segmental display ABCDF is shown here in this particular circuit. So next we are going to see here, this is the 0. This is the once we are going to give the values, then automatically the 0 value can be displayed on 7 segmental. To say this is B and C, only 2 segments are glowing here, and A, B, this is G and D, E. So if these things are glowing, then automatically we are going to get 2, and this is A, B, C, D and G are glowing, then we are going to get number 3, and here F is there, and B, C, G, F. If only these 4 segments or LEDs are glowing, then we are going to get an effect of or symbolic representation of 4 we are going to see here. Similarly, this A and F, G, C and this D are glowing, then we are going to get an effect of 5. Then except this particular B, if you are not it's switched off or it is not glowing, then if all other remaining 6 segments are glowing or LEDs are glowing, then we are going to get the effect of number 6. Similarly, this A, B, C, only these 3 are made to glow and all other segments are going to switch it off, then automatically the segment, this number 7 can be generated. If all the segments are made to glow, so then automatically the number 8 can be displayed. So next only this particular E value, so this particular E segment, if you are if you stop glowing, then automatically the remaining part of the segment glowing is going to indicate the number 9. So this kind of a thing, it is possible for us to generate just by varying the values of ABCD, just by changing the values what we are giving as an input ABCD. If you are going to change, then automatically 0 to 9 numbers can be generated. Display decoder circuit operation. The circuit operation can be understood through the truth table. Already we have discussed, when all the inputs are connected to low logic, the output of the combinational logic circuit would be so as to drive all the output LEDs except G to conduct for conduction. Thus the number 0 will be displayed. So already that 0, how the 0 is displayed, we have discussed. Similarly, operation would take place for all other combinations of the input switches or ABCD variable values. So now the application part of this display decoder circuit, this circuit can be modified using timers and counters to display the number of clock pulses. Just by giving a clock pulse, it is possible for us to count how many number of clock pulses we have given. So this circuit can be modified to develop an alphabetic display also. So here instead of ABCD can also be generated by suitably selecting which RM should which segment should glow and which segment should not glow to indicate the alphabetical things like ABCD up to Z can be generated. And the last one, it can be used as a timer circuit. Just if proper circuit is designed as a timer circuit and with proper clock pulses, and such clock pulses are given to ABCD as a input for inputs, then automatically this circuit can be used as a timer or clock circuit, just to, that is the event monitor purpose, and in speed, okay, measurement, how many this any sports events, if a stopwatch type of construction can also be done by suitably incorporating this circuit for our requirement. So now let us complete this session, and for further clarifications, for any mistakes in the slight mistakes may be there here and there, for such type of clarifications you can meet us through email goody_anand@rediffmail.com, and my mobile number displayed 9448240 189. That is, thank you. With this I conclude my session.